Welcome to Ask and Learn.
Here we have a position equation, and for part A of the problem we want to find the velocity. Remember that velocity is the derivative of position, and because our position equation is a quotient, we're going to find the derivative using the quotient rule. So here we have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Next we need to simplify that. So what I've done is distribute the 9 and multiply the 9t and the 2t. And then I combine the like terms. So that's our velocity. For part B, we want to find the velocity at time 1. So we're going to substitute a 1 in for t and then simplify. And we end up with 18/25, and the units would be feet per second. For part C, we want to know when the particle is at rest. And a particle is at rest if its velocity is equal to 0. So we take our velocity, we set it equal to 0, and we solve for time. Now when you have a fraction that equals 0, you want the numerator to equal 0. And when you look at this denominator, you'll notice that there's no real number that makes it equal to 0 anyway. So we set the numerator equal to 0, and we solve for t. We can add 9t squared to both sides. Now we have 9t squared equals 81. We can divide both sides by 9. Now we have t squared equals 9. And we can square root. And typically we would write plus or minus 3, but because for this problem we're starting at time 0 and only using positive times, we're not going to include negative 3. Okay, so now we know the particle is at rest at time 3 seconds. For part D, we want to know when is the particle moving in the positive direction. And it will be moving in the positive direction if the velocity is 0. So what we do is we take the information from the previous part. We found out that the velocity was 0 when the time was 3. And what we do then is we make test intervals before 3 and after 3 to figure out what the velocity is doing. So before 3, we have the interval from 0 to 3. And after 3, we have the interval from 3 to 0. So what we want to do is pick a number in each interval and test it into the velocity to see if we get a positive or a negative. So I picked 1 and I picked 4. And remember back in the previous part of the problem, I think it was part B, we found that v of 1 was positive 18/25. So we know that v of 1 is positive. And then if you substitute 4 into the velocity, you get a negative. So what this is telling us is that the particle is moving in the positive direction from time 0 to 3, and it's moving in the negative direction from time 3 to infinity. For part E, we want to find the total distance traveled by the particle from time 0 to time 6. So here's what we just learned. We learned that it's traveling in the positive direction from time 0 to time 3, and then it's traveling in the negative direction from time 3 to time 6. So what we don't want to have happen is we don't want a negative to cancel out the positive distance. And so we're going to take the absolute value of each distance. We're going to break it down into the distance from time 0 to time 3 and the distance from time 3 to time 6 and take the absolute value each time. So to get the distance from time 0 to time 3, what we do is we find the position at time 3 minus the position at time 0, and then we take the absolute value. And to get the distance from time 3 to time 6, we take the position at time 6 minus the position at time 3, and then take the absolute value. Now those position values come from the original function f of x. So if you need to find f of 0, f of 3, and f of 6, you can substitute those into your f of x function. And you can use the table feature of your graphing calculator to do that. It's really helpful. So those numbers go in, so we have the absolute value of 1.5 minus 0 plus the absolute value of 1.2 minus 1.5. And that gives us the absolute value of 1.5 plus the absolute value of negative 0.3. And so we have 1.5 plus 0.3, so the distance traveled is 1.8 feet. Now we're going to make a motion diagram. And because we know it went in the positive direction for a while and in the negative direction for a while, we should see that in our motion diagram. So what we see is the particle starting at time 0, position 0. It moves to the right, and it stops moving to the right at time 3, and then it moves to the left. For part G, we want to find the acceleration. And remember, acceleration is the derivative of velocity. So we had our velocity equation. Now we take the derivative of it using the quotient rule, and we get our acceleration equation. So here we have the bottom times the derivative of the top minus the top times the derivative of the bottom, using the chain rule to do that, over the bottom squared. That's going to need to be simplified if we're going to be able to use it for anything. So I distributed and multiplied these together. Actually, no, I did not distribute. What I did was I factored out a t squared plus 9 from here and a t squared plus 9 from here, and I canceled it with one of the t squared plus 9s on the bottom. So that left me with what we see in the next step. And then I distributed. So I multiplied the 18t by t squared plus 9, and I multiplied the 4t by 19 minus 9t squared. And once we have that, we can combine the like terms. And then I decided after that that I would factor out the common factor of the numerator, which was 18t, because I'm anticipating that eventually we're going to get to the point where we have to set this equal to 0, and I thought it would be easier if it was factored. Okay, the next thing we want to do is find the acceleration at time 1, so we substitute 1 into that acceleration function, and we can simplify it, and we get negative 117 over 250, and the units would be feet per second squared. Now that we have the position, the velocity, and the acceleration, we can use a graphing calculator and look at all three graphs. So we go to the calculator, we go to the y equals menu, we type them all in, and now we need to set a good viewing window that's going to allow us to see all of these. So think back over some of the numbers we got from the previous parts of the problem. Like we found out that the positions were numbers like 0 and 1.5 and 1.2. We found out that times were numbers like 0 and 3 and 6. So based on that, I went to Window and I decided to try letting my x values go from negative 1 to 10 and letting my y values go from negative 2 to 3. And you can always fiddle with these numbers and make changes until you like what you see. So what we have here, the blue one is the graph of the position equation, the red one is the graph of the velocity equation, and the black one is the graph of the acceleration equation. Okay, after that, the final part is to find out when the particle is speeding up and when it's slowing down. And a particle will be speeding up if its velocity and acceleration are both positive or both negative, and it will be slowing down if its velocity and acceleration have opposite signs, one with a positive, one with a negative. So we need to figure out when our acceleration is 0 so that we can then figure out when it's positive and when it's negative. So we take our acceleration and set it equal to 0, and you'll notice here that I just have the numerator, because if a fraction is equal to 0, it's just the numerator that's going to equal 0. And so then we can set each factor equal to 0, and we can solve each of those, and we end up with t equals 0 or t equals 3 square root 3. And we're not including the negative time, of course, because we're only talking about time starting at 0 and going forward. Okay, so what we're going to do once we know the times that the acceleration is equal to 0 is break the number line down, and we're going to find the acceleration between time 0 and time 3 square root 3, and we'll find the acceleration between time 3 square root 3 and infinity. So what I did was I plugged in a number into the acceleration. I plugged in a number that was in the first interval. We had already plugged in a 1, so that's convenient, and it turned out negative. And then I took 10, a number that was in the second interval, put it into the acceleration, and I got a positive. So now let's bring that information together with the information from the velocity. So I'm breaking down the intervals, and I've broken down the intervals at 3 square root 3 because that is where we see the change in acceleration, but I've also broken down the intervals at 3 because that's where we saw the change in velocity. So what we saw with velocity was it was positive between 0 and 3, and it was negative after that. What we saw with acceleration was that it was negative before 3 square root 3 and it was positive after that. So based on that, when the signs are both the same, negative and negative, we know the particle is speeding up. So it's speeding up from times 3 to 3 square root 3. And when the signs are different, a positive and a negative, we know that the particle is slowing down. So it's slowing down between times 0 and 3 and times 3 square root 3 and infinity.